Thanks for coming to my talk. It's been a great conference so far. Hope you're all enjoying it too. Before we get going, I want to ask a couple of quick questions. How many here, raise show of hands, have worked with or are familiar with Kafka, Apache Kafka? Okay, so some there. That's good. How about have you done any data stream processing with Kafka? Or familiar with that? Okay, so that's what we'll be talking about in this talk today. So one last question: how many of you hate being asked to raise your hand in conferences? Me too. All right, so we'll get going. My name is Dave Klein. I'm with Quix, a company that provides a full stack data streaming application platform for Python developers, as well as a open source library called QuickStreams, which hopefully I'll be able to mention at the end if I don't run out of time, which I might do because it's a very short time slot. All right, so we're talking about stream processing, so quickly define what I mean by that. This is not stream process like streaming video or audio. This is talking about data streaming. So I like to use the term event streaming. I think the term events is really helpful to understand that all data that comes into our applications, whether it's coming from applications, mobiles, IoT devices, CDC from a database, wherever the data is coming from, something happened to cause that data to exist. That was an event. And so that's why I like that logical concept. But also you'll hear the term message or record, and those are valid as well. It's all just data. It's all bits and bytes. And so that data comes into our applications in high volumes and at high speeds sometimes. And we can collect that data, pile it up in a database, and then periodically pull it out and do something with it, or we can respond to it as it arrives, right, in real time. And that's what we're going to talk about here, to do real-time processing on our data to be able to take advantage of it more quickly. So this block in the middle is that's going to be our processing application, which is at its heart is going to be a broker, and we'll talk about that in a second too. So what we basically do is we have data coming in. The basic concept of event stream processing is data comes in on an input, it's processed, and goes out to one or more outputs. So that's what you see there, downstream processes. You may just process it and store it. You may process it and pass it on to a UI, like a dashboard, or off to a business intelligence program or something else. So as I said, at the heart of this is a broker. I think Apache Kafka is the de facto standard broker these days, but there are others out there like Apache Pulsar, Red Panda, Amazon Kinesis, and a bunch of others. But again, the lion's share of the market is Kafka, and it's my favorite, so that's what we'll talk about here. And then there's also the applications that do the processing. So there are applications like Apache Flink, which is probably one of the most popular ones, KSQLDB. Now these are applications that you run in their own cluster, and you build jobs on them, and you execute those jobs to do your stream processing. But these are extra infrastructure. Someone has to deploy it, someone has to manage it. So another alternative is libraries. The most popular one of those is Kafka Streams. And that's a JVM-only library, so it works with Java and any other JVM language. But it's still extremely popular, and even a lot of Python developers end up having to break down and learn Java just to do that. So we're hoping to free them from that. But I am going to be using some examples from Kafka Streams. Kafka Streams comes with a DSL, which gives you some functions that you can do common stream processing functions with this simple DSL. And so we're going to model that with Python code in here. But there's a bunch of others as well as other libraries that are less common, and there are also libraries in other languages. We'll talk about some of those. Okay, so real quick, Kafka Primer here. I would love to do more on this, but I just don't have the time, so I'll just give you a real brief overview of what Kafka is and how it works. So at the heart of Kafka is a topic, which is a log. A topic is actually made up of multiple logs called partitions, and that's for scalability, and we'll mention that a bit in a minute. Some key things about these logs of data are that it's immutable. And again, that's why I like events, because events are immutable, right? An event happens, you can't unhappen it. So it's immutable, it's append only, you just add new data as it comes in to the end of the log. You can't shuffle it around or sort it or change where you insert things, nothing like that. It's always appended at the end. And it's always ordered, it's processed in the order that it's added, and it's durable. So unlike a queue where data is read and then removed, the data in a Kafka topic stays there as long as we want it to. Right? So we set retention periods with either time or size on disk, and that determines how long the data stays there. So which is really nice because it can do things like replaying. You find a bug in your code, you fix it, you replay your processes, and get the better results. Also, it means that other applications can use the same data. Here's an example of a typical Kafka event. The main things you're going to see in here are a timestamp, a key, and a value. There's also headers you can add and some other things like that, but these are the main components that you'll work with. The key is usually a simple data type, like a string or a long, maybe a UUID. And then the value is where you have your payload. That's your object usually. And these things are written to the Kafka topics by a producer. A producer is part of the client library. The client library that comes with Kafka is, again, a JVM library. but there are libraries in other languages, including a few for Python. And the thing that reads the data off of the topics is a consumer. Now, these consumer producer are completely decoupled. They don't know anything about each other. So this is earlier, I think yesterday there was a talk on event-driven architecture, and it's the same concept there. So you have that decoupling between the sources and the users of the data. So these things are completely decoupled, but they're both part of the same client library. So they're just classes you include in your applications. And there's numbers you see at the bottom of that thing there. Those are called offsets, or represent offsets. An offset is a number is uniquely assigned to every event that lands in a topic. And it stays with that event as long as it's there up into the retention periods. Those numbers are not reused, so that number's always unique. So you can use that to seek to a specific offset and move on from there if you need to replay something. Also, it's used by consumers. If a consumer crashes, it keeps track of where it left off. That's what it says, you have a committed offset. And you do that in your code periodically, either explicitly or you can set it to do it automatically. It'll log how far it's gotten in its process so that if it crashes, it knows where, and it starts up again later, it knows where to pick back up on. This reduces the likelihood of duplicates. It doesn't eliminate it, but reduces it. But it mainly makes sure that you don't skip anything. Okay, so one more bit on Kafka is the consumer groups. And there's so much more to say about Kafka, but I just want to give a real brief overview. So consumer groups allow us to have multiple instances of our consumer applications, because normally producers produce faster than consumers consume, because consumers have to consume the data and do something with it, right? So you can add multiple instances or run multiple instances of your consumer application. They will be automatically combined into a group using a group ID, which is a configuration setting we'll see in a bit. And then the workload will be spread across them evenly, automatically for us. So here we have 2 instances of our application. We have 4 partitions in our topic, and so each of them gets 2 partitions to work with. If we get busy, we scale out to 4 instances, and then each one gets 1 partition, and that happened for us automatically. If things slow down again, we go back to 2, and it again rebalances for us automatically. So it's a really cool feature of Kafka and consumer groups. All right, so that's the end of our Kafka Primer. So the Kafka clients that would have all this goodness in them are the ones for Python. They're most common out there are the Kafka Python library, which is a community-based library. There's Confluent Kafka, which is produced by Confluent, the company that's founded by the original creators of Kafka. It's a company I used to work for too, so I'm going to use their example because I'm more familiar with it. And then there's AIO Kafka, which is an async library, which I haven't used yet, but I've heard good things about. And there's others out there as well, but these seem to be the most popular. All right, so how to use those in our Python applications. Here's some very simple examples of a producer. To import the producer class. The constructor just takes a dictionary, and there's a bunch of configurations you can put in there, and they're all online. You can read about them later. But the main one you have to have is Bootstrap servers, which tells you where to find Kafka. That's the important part. And then all we do is when we're getting some extra data from some external system, supposedly. But then we just call producer.produce. And the produce call takes the topic name that we want to send it to, and then the value that we're sending, and then the key. So those are the 3 parameters. There are other parameters you can add as well, but these are the main ones. And then producer flush just make sure that it's all really completed and acknowledgments received. Normally you call flush after a series of produce calls, but I just want to show it here on the slide. Consuming is very similar. Import the class. The constructor here, the dictionary in this constructor has 2 required parameters or properties. One is the Bootstrap server again, which is a node on the Kafka cluster. It's interesting to note you only need to get 1 node. Normally Kafka is running a cluster of multiple nodes. You only need to point to 1 node. Once it connects to that one, you'll get metadata about all of them. But the other thing we need here is a group ID, and this is for the consumer groups that we talked about earlier. And then with the consumer, there's an extra step, but we have to subscribe to a topic. With the produce, we told it what topic to send the data to. With the consumer, we need to say what topic do I want to basically listen to. So you subscribe to a specific topic, and then every time you call poll, we jump down into a loop here and we start calling poll. Every time we call that, it'll check that topic for new data. And the timeout just tells it how long to wait. If it gets data, it returns instantly, but if there isn't any data yet, it'll wait up to the timeout for data to come. And then if there's no data, it'll return none. So we grab the data. We have to decode it because the data in Python or in Kafka is always bytes. So we serialize it to bytes to send it to Kafka. We deserialize it as we're reading it off. So we're going to decode that value, turn it into a JSON object, and do something with it. So normally there'd be a lot more that we would do with that, but that's the basics of producing and consuming data to Kafka. Now this produce and consume concept is going to be reused, and we talked about streaming, but yeah, we'll get to that. So with stream processing, you're basically going to do is you're going to consume from 1 or more input topics, you're going to do some processing, and you're going to produce to 1 or more output topics. So you're going to be using that consumer and producer in there. And there's streaming libraries out that will encompass that for you, but you can do it just using those classes themselves, which we'll see next. Okay, so we'll talk about two main types of processes in stream processing: stateless and stateful. The stateless ones are the simplest ones, and so those are the ones we most likely don't need, or more often won't need a library to help us with them. So they're really simple, but the examples I'm showing here are ones that are in the Kafka Streams DSL, so that's why I'm using them as a model. And so the first one's filter, which basically takes a stream of data, filters out stuff we don't want, and just keeps the stuff we do. So we subscribe to our input topic, we jump in our event loop, and we just check a predicate. And if it matches, we send that to the output topic. I mean, it's kind of basic, but that's what filter would do in Kafka Streams. It's important to note that the data still stays in the input topic, so we're not removing any data or losing any data. Our output topic will have less. It'll have just the things we want for our specific purpose. And you can stack multiple filters on there to do a branching mechanism, where you could send one input stream can be split out into multiple output streams using just stacked filters. And in Kafka Streams, there's actually a branch operation, but it basically does the same thing as a stacked filter. So that's the filter example. Map is another really common function in the Kafka Streams DSL. And with this, we go through our input topic, and everything that comes through that stream, we're going to perform some function on it. And so we define a function for that. We just jump into our loop like we did in the last example, and just call that function to transform it, whatever we're going to do with it. Maybe strip some data out, maybe mask some PII, or flatten some data, or whatever transformations we need to do with that, we'll do that, and then get that return value, and then produce that to an output topic. Generally, we'll use the same, well, not generally, often we'll use the same key as the incoming event, but sometimes, and actually a relatively common use case for map is when you have data coming into Kafka that doesn't have a key, because keys are optional, but they're very valuable and helpful. But sometimes you have data coming without a key, like say a QuickStream or something like that. So you can use map to pull every event in, grab some field out of the value, and use that as a key, so the downstream data will have a key. So that's another common use for map. And now let's talk about stateful operations. These are the ones that get a little bit trickier, and because we have interim state to keep track of. And I'm going to use some simple examples where the state's not that hard to keep track of, but state can be very, very difficult to keep track of. And state also produces a lot of edge cases and traps. And we'll talk about that more later. So in this situation, we have all our stuff. I'm kind of just assuming we have all the things we saw earlier with the producer and consumer. But we set up here a dictionary called counts. We're going to do a count here, which is our first example of a stateful operation. And so just jump in our loop again like before. We consume from our input topic, and we check to see if the key to that of the event that we just consumed is existing in the counts dictionary. If that key is already there, we'll grab the value based on that key and add 1 to it. If it's not there, we'll add it to the dictionary, and the initial value will be set to 1. And so we keep running through that, and that keeps an ongoing count of that key showing up in our event stream. And then as we go, for each step, we produce an output topic. The output topic will have the key and the current value of the count. So the output topic will have a running total for every key, and so you can feed that to a dashboard or something like that. In fact, in my example, I don't know if anyone's seen this, but I've been running a little top tweeters leaderboard for people tweeting about the conference here. I've been using count for that. So that's counting, and we can use the dictionary to hold the interim state. Oop, I'm running out of time. I'm faster now. So the next one we do is summing, which summing is basically could be an example of any kind of aggregate, really. You want to do an aggregation function. So we're going to we're going to loop through it again. We're going to set up a sums dictionary. If the key exists there, we'll pull the current value, the current sum, out of the dictionary based on the key, and add the new incoming value to that, and that increases the sum. And then if it's not there, then we add it to the dictionary and set the current value as the initial value, the initial sum. And it keeps on building up as that. And again, at each step of the way, we produce it to the output topic. So that's summing. And then the more complicated one is joins. I won't spend a lot of time on this because the slides will be available after if anyone wants them. But basically what we're doing is we're pulling from 2 different input topics, and we're going to find a match on keys and join those together to create a new object that's going to go into a 3rd output topic. So we have 3 dictionaries, A dictionary, B dictionary, and C dictionary, and we have 2 consumers, consumer A and consumer B. So we start with A. We can call consumer A poll. We get the event. We add that event immediately to the A dictionary. And then we check to see if the key to that event is also in the B dictionary. If it is, but it's not in the C dictionary, if If it's not in C yet, that means it hasn't been joined yet, but B is there, so we have A and we have B, we can do the join. So then we go ahead and do the join. And the join function would be something you would write that would just pull data, pull whatever pieces you needed from each of the two different objects, right? The one from A and one from B, put those together into some new object, and then, or maybe you need all the values from both, that's fine too. Whatever combination you need, you do that in your join function, and then produce that object and send that one to the C dictionary, or as the C event. And then the C event is written to the C dictionary, so that we know that it's already there, so we won't do it again. But if it wasn't there, then we go down, we pull on B next, and if we get the B value, we put that in the B dictionary, and then we check to see is this already in the A dictionary, but not in C yet. And so we don't know what order they're going to come in. So the object, the matching key might come in A first, it might come in B first. And with this process set up here, it won't matter. It'll eventually find the match. There's also no time limit on this. Most streaming libraries would have a windowing operation where you set the time, how long it'll wait for a match. This one just will wait forever, which isn't realistic, but it's a simple example. You could do things to clear out the dictionary periodically based on a timer or something too. But once you find the match, then you write that match either in the first block or the second block. You're going to write the match out to the C dictionary, and then you're going to produce that to the output to the C topic. Or your output topic is going to have the C value. So you've done your join, your new value goes to the output topic. So that's the join. So that's the overview of some examples of some stream processing. There's a lot more I could have given, actually more I had, but I had to cut them out because of the time limits we have here. But there are some challenges that we run. Oh, and I did have a demo I was going to do. I don't have time for it, but there's code there if you want to check out the code for it. This is the code I'm using. It's actually 3 little applications that I'm using for my top tweeters that I've been posting on Twitter throughout the conference. And that gives us this. So this is pulling a list of the people who have been tweeting the most about PyCon Italia, and that's the count. And I'll send an update to this later on today too. But it's been fun posting that along the way. But that's using the application you can find on GitHub, and that's using some examples of some of the things we do there. I've got a couple of filters and a count that I'm using in that application. But there's some challenges with stream processing like this, okay? They come in 2 main things. State is the first one. We talked about that already, because we use those dictionaries, and that works fine. You can use dictionaries or lists or other things to hold state interim while you're processing. But those are variables. They're going to go away if your application shuts down, right? And then you've lost your state, and that could be a challenge, a problem. There's ways you could store it off, somewhere else and reload it later, but those are all things you're going to have to manage. And these are the things that most of the libraries that are out there will do for you. So state is one of the challenges. The other is scale. If we ran this, think about the consumer groups we talked about earlier. If we ran multiple instances of our application, then they're going to have multiple copies of those dictionaries or lists or whatever we're using to hold our state. So those are all going to get scrambled, and they're not going to be joined in together to one thing, and it can be difficult to manage that. So again, the stream processing libraries will help you with those things too. So there's a lot of situations, and I like the principle of do the simplest thing that could possibly work. And so there's a lot of situations where what I just showed you, these simple processes would work fine. So we can take, as Python programmers, we can take advantage of event streaming easily in a lot of situations. And there's sometimes when it's really helpful to use those techniques. But if we do run into these other challenges, then there are libraries out there to help. And there's a few of them here. QuickStreams, which is the one that's put out by the company I work for. It's open source, and you can find it in the GitHub repo there. Faust is another one that's been out for quite a while. It's originally started by Robinhood, then they kind of dropped it and it got forked. So it's kind of going by the community. I'm not sure how much it's moving forward, but it's still out there. Or like we just showed, you can do it yourself. And I think there's some others out there too that are popping up more recently. But these things, the one thing that different libraries will have in common is that they will help you with those 2 challenges, state and scale. And here's a quick example of how it would look in what was the time on that one? Okay, thank you. So here's a quick example of how QuickStreams would help us. This is a different example in here, but here it's a food delivery process we're running. But rather than having a consumer and producer created with our constructors, we actually start off with creating this Kafka streaming client. And that will encompass our producer and consumer for us. So we can get those by calling these methods on there to get our consumer, get our producer. We're giving it things like the input topics and output topics, and our consumer group. And then we can set up, basically we set up callbacks for these. So we set up a handler that's going to handle the data as it comes in. So every time data comes in, this method will be called, and it'll do some calculations. One of the cool things with QuickStreams is it integrates with the integration with data frames. So as data comes in QuickStreams, it'll automatically load into a data frame which you can use in your applications. So that's what we're doing. In this situation here, we're calling the data frame, we're just calling another function to calculate ETA. This is a food delivery thing. So we're taking the data that we have already, using that to calculate an ETA, and then adding that to a new column of the data frame, and then putting that as the output. So basically, we're getting data in, we're enriching it with a new estimate on a estimated time for delivery for the food, and we're adding that to the output so that it goes downstream and it can be passed off to the mobile app or whatever it needs to tell people how long it's going to take their food gets there. So this is handled, this one we're not dealing with state in this example here, but this was dealing with scale by using a stream ID. So you see up here the stream.stream ID, that is actually going to be based on the key for the objects we're working with. And so everything having to do with that order is going to have that same stream ID, and so it'll always be in the have the same key, which means it'll go into the same consumer group, so it'll always be kept in sync. And so that handles the scale. We can have hundreds of instances of this application here running, and it would all keep track of the different delivery drivers, orders or whatever in sync. And we don't have to think about it. It all handles automatically, scaling up and scaling down. So I could go into more detail on that, but that's like I said, the two key things that libraries will help us with are state and scale, and QuickStreams is one that really helps with that a lot. And you can find out more about that at the GitHub repo. There's a lot of information out there on that. And that's all I had. Yeah. So I mainly wanted to get across the idea that event streaming like this is not as complicated as some people make it sound. When you think about all the libraries that are out there that you have to use, or applications like Flink or those things like that, you think, wow, this is just too complex. But it really isn't. It's really pretty simple, very powerful, but pretty simple at its core. And you can grow the complexity as you need to, but you can start with simple steps and go from there. Now, this QR code here, if you scan that, you can enter a contest for a €50 Amazon gift card. Or you can also scan the back of my shirt if you missed this slide. But please do that. And we'll announce the winner this evening online. So on Twitter or LinkedIn, we'll post the winner. And also, there's my email down there. You can feel free to contact me anytime. And we also have a forum.quicks.io. So I encourage you to check out that forum. You can post questions to me or to anybody else about event streaming in general, about Kafka, lots of things like that. You can post on that forum, and you'll get answers pretty quickly. And that's all I had, so thank you very much.
Thank you, Dave. That was wonderful. Now, there are obviously some questions here for you. Yeah. So, is there an easy way to get it up and running without Zookeeper?
Yeah, the most recent versions of Kafka will run don't require Zookeeper. So if you get the latest versions of Kafka, you can run those just on its standalone. And they're even working on easier ways to run it as a standalone executable using Graal VM, I think. But I don't think that's out yet. But it will run without Zookeeper. But even with Zookeeper, there are easy ways to get up and running using Docker. There's a lot of public Docker container or Docker images you can use to load things up like that real quick and easy.
All right, thank you. Next question is, a problem with the state is that it's in memory. If the processor goes down, your state is gone. Could you store the state in a log topic as well? Log/topic as well?
Yes, you can. In fact, that's the way Kafka Streams does it. It stores it temporarily in RocksDB, but then it writes that to a different Kafka topic, a changelog topic. So you can do it that way. You can do file system. In QuickStreams, we have it set up to run local, so you can run it in if you're running in Kubernetes, you can run it in your local storage and store it there. So it's a little bit faster to get to and from that way. But yeah, there's different ways. And we covered the state issue later, but yeah, I guess the question came before then.
Very many questions for you. Yeah. Would you mind providing some real-life cases example for count, sum, join, stateful operations, please?
Well, real-life examples. There's tons of them out there, but for example, data coming in from orders online, and you got keys in there like order ID, customer ID, things like that. You need to join that up with real data to flesh it out, to do something else with it downstream. So you might join your data with your incoming data with another stream that has the lookup information basically, and enrich your data that way. Counts, I mean, they're always accounting things. I mean, getting the latest number of sales for something, getting attendees at a conference. You could be tracking as they're signing up. I used to run a conference, and we used to do that a lot because you're always worried about whether they're getting enough attendees. So there's lots of uses for counting things like that. So, but for real-time processing in general, the use cases are growing all the time. You think of things like recommendation engines or things like that. The more quickly you can process the data to update those things, the more valuable it's going to be to the end users.
Okay, next question says, and it's by Dave. So I I developed cloud-based application on AWS. Why should I use MSK instead of the standard AWS IoT Core MQTT broker and Amazon Kinesis for processing? I don't know if I pronounced that wrong.
It's really up to you. They do basically the same things. I think Kafka's a bit more robust and faster than some of those other options. It also probably has a wider ecosystem for support. But if you're solely on AWS and you're just using AWS for everything, then it might make sense to stick with their native technologies.
Still not done. Can something like Redis be a good solution to handle state?
Yes, actually, that's some people do use Redis for a state store. As I mentioned before, Kafka Streams uses RocksDB by default, but it's pluggable, and I've known people who have used Redis, plug Redis in for that instead. So it can be used for that.
Last one. Okay. What do you think of Pulsar as an alternative to Kafka?
Well, it is an alternative, and it's up and coming. There's trade-offs and different things that it can do better than Kafka and things that Kafka does better than it. So it's really a matter of your use cases. I would try out both for what you're trying to do and see which works best. The other thing too is that Pulsar is gaining some traction, but there's still nothing like the community and resources around it that there is for Kafka.
All right, thank you very much, Dave. Can you please, yeah.